The space between stars is not empty at all. It is the most deceptive illusion in the cosmos. What looks like a serene, black void is actually a seething, dynamic sea of potential. This is the quantum vacuum, the most fundamental and mysterious arena in all of physics. By the end of this journey, you will see the fabric of reality in a completely new light. We are about to dive into 25 profound mysteries hidden within this nothingness. These are not small puzzles. They are the grand questions that define our universe, from the explosive moment of its birth to the mysterious force tearing it apart. How can nothing have so much energy that it threatens to rewrite physics itself? What if the empty space around us is just a temporary illusion waiting to pop? We will explore mind-bending concepts, but we will walk through them together in a fun and relatable way. The stakes could not be higher, because to understand the vacuum is to understand everything. So, are you ready to question what you think you know about nothing? This deceptive nothingness holds its first and greatest secret. The quantum vacuum is not just a stage where particles perform. It is the performer. According to quantum field theory, the most accurate description of reality we have. Every point in space is a seething ocean of energy. Think of it like this. Imagine a calm pond, its surface perfectly smooth and still. This is the classical idea of empty space. Now look closer at the microscopic level. That smooth surface is actually a chaotic frenzy of tiny waves, constantly appearing and disappearing, jostling and bubbling with an energy that can never be stilled. That bubbling is the vacuum. Even at absolute zero, the temperature where all classical motion stops, this quantum jitter remains. This is called zero-point energy, the lowest possible energy a system can have, and it is emphatically not zero. It is the hum of existence itself. We know this is real because we can see its effects. Take two tiny, uncharged metal plates and place them incredibly close together in a vacuum. You would expect nothing to happen, but something does. They are gently pulled toward each other. This is the Casimir effect. The reason is poetic. In the empty space outside the plates, virtual particles, fleeting fluctuations of the quantum field, can pop into and out of existence in all sorts of wavelengths. In the narrow gap between the plates, only certain wavelengths can fit. This creates a pressure difference pushing the plates together. The vacuum itself is doing the pushing. So the energy is undeniably there, but here lies the colossal mystery, a problem so severe physicists call it the worst theoretical prediction in the history of science. When we try to calculate how much energy this quantum vacuum should contain, the number is absurd. It should be about 120 orders of magnitude larger than what we observe. That is a 1 with 120 zeros after it. If the vacuum energy were that strong, the universe would have ripped itself apart in a fraction of a second after the Big Bang. Space would have such violent repulsive force that not a single atom, not a single star could ever form. Yet here we are in a stable, expanding cosmos. So what gives? Why is the vacuum energy we measure so infinitesimally small compared to the vacuum energy we calculate? This is the cosmological constant problem. It means we are either dramatically misunderstanding the vacuum, or there is some miraculous, perfect cancellation happening that we cannot explain. The nothingness is hiding something fundamental, and our first clue is that its energy is missing. This staggering mismatch is not just a small error. It is the single greatest discrepancy between theory and observation in all of science. The energy of the quantum vacuum should act as a cosmological constant, a relentless pressure woven into the fabric of space itself. According to Einstein's equations, such a constant would produce a repulsive force, causing the universe to expand at an ever-increasing rate. And indeed, our universe is doing exactly that. We call the driver of this acceleration dark energy. So far, so good. The vacuum could be the source, but then we do the math and everything falls apart. When physicists calculate the expected energy density of the quantum vacuum, using our well-tested quantum field theories, the number they get is beyond enormous. It is roughly 10 to the power of 120 times larger than the value we actually observe for dark energy. To grasp how wrong this is, imagine predicting the weight of a single grain of sand, and your calculation gives you the mass of the entire observable universe. That is the scale of our failure. This is why it is often called the worst theoretical prediction in the history of physics. The problem is a nightmare because both sides of the equation seem unshakable. Our quantum theory works spectacularly well for explaining the world of particles and forces, and our astronomical observations of distant supernova and the cosmic microwave background are incredibly precise, firmly establishing the tiny amount of dark energy that shapes our cosmos. So we are left with a paradox that cuts to the core of reality. Is our mathematics for the vacuum fundamentally flawed in some way we cannot yet see? Could there be some exquisite hidden cancellation mechanism where positive and negative contributions from different fields perfectly balance out to nearly zero, leaving only the faint whisper we detect? Or is the most logical answer the most unsettling one? Perhaps dark energy is not the energy of the quantum vacuum at all, but something else entirely, a new kind of field or a modification of gravity itself. The emptiness is not just hiding its energy, it is forcing us to question whether we understand the most basic tools we use to describe the universe. This missing energy is not a quiet mystery. It screams at us from the cosmos itself, driving its most dramatic behavior. The universe is not just expanding. That expansion is speeding up, as if some invisible force is pressing harder and harder on the gas pedal. We call that force dark energy, and it makes up about 68% of everything in the cosmos. Its behavior is eerily familiar. It acts like a constant, uniform energy density spread throughout all of space, pushing galaxies apart. That description should ring a bell. It sounds exactly like the cosmological constant, the energy inherent to the quantum vacuum. So the most straightforward, almost beautiful idea is that dark energy is simply the energy of empty space, finally making its presence known on the grandest stage. The math of its effect matches perfectly, but here is where the mystery deepens into something far more unsettling. Remember that catastrophic calculation, the one that says the vacuum energy should be unimaginably larger. Well, the tiny sliver we see as dark energy is not just small, it is suspiciously small, and it has a very specific constant value. This leads to a chilling question. What if our vacuum, the one that seems so stable and allows for atoms, planets, and life, is not the true, final state of nothingness? What if it is a false vacuum? Think of it like a ball resting in a small dip on the side of a much larger hill. It seems stable, but it is not at the bottom. Given a big enough nudge, it could roll all the way down into a deeper valley, a state of true, lower energy. In cosmic terms, our entire universe might exist in that shallow dip. The quantum fields that dictate reality might be temporarily trapped in a configuration that is not their absolute lowest energy state. This is a stable illusion, but an illusion nonetheless. And if that is true, then somewhere, at some point, a quantum fluctuation could provide that nudge. A microscopic bubble of true vacuum could spontaneously form. Inside that bubble, the laws of physics would be different. The constants we rely on, like the strength of gravity or electromagnetism, could be rewritten. This bubble would then expand at the speed of light, its wall a wave of total cosmic transformation. Everything it touches ceases to exist as we know it. There would be no warning because the change propagates at light speed. One moment our universe is here, the next it is gone, replaced by a new reality with new, unknown rules. This is the hypothesis of vacuum decay, a cosmic doomsday scenario born directly from our contemplation of nothing. It suggests that the ultimate fate of everything might not be a slow fade into darkness, but a sudden, irreversible rewrite of existence itself, triggered by the quantum instability of the empty space we call home. The possibility of such a cosmic reset is terrifying, yet it stems from a phenomenon that is both mathematically elegant and utterly bizarre. This brings us to our next pair of mysteries, which are two sides of the same quantum coin. To understand the vacuum's power, we must meet its most famous inhabitants, virtual particles. The principle at work is the Heisenberg uncertainty principle, a cornerstone of quantum mechanics. It tells us that for a very brief moment, energy does not have to be conserved. A particle and its antiparticle can spontaneously appear from the vacuum, borrowing energy from the nothingness itself. But they must repay that energy loan almost instantly, vanishing back into the void in a time so short we can never directly catch them. Think of it like a cosmic version of static on an old television screen. That snowy, chaotic flicker is not just noise, it is a glimpse of the vacuum's ceaseless activity, a sea of these temporary particles bubbling everywhere. Now, if we can never see them directly, how do we know they are real? Because they leave fingerprints everywhere. One of the most beautiful examples is called the Lamb shift. When scientists measured the fine structure of hydrogen, the energy levels of its electron, they found a tiny discrepancy from what classical physics predicted. That tiny shift is caused by the electron constantly interacting with the virtual particles popping in and out around it. The vacuum is not empty. It is a frothing medium that slightly alters the behavior of everything within it. An even more dramatic effect gives us Hawking radiation. At the very edge of a black hole, the immense gravity warps spacetime so severely that a virtual particle pair can be torn apart. One falls into the black hole while the other escapes into space as real radiation. To an outside observer, it looks like the black hole is slowly evaporating, glowing with a faint heat generated by the vacuum itself. So these fleeting ghosts have real, measurable consequences, but this leads to a profound and heated debate. Are virtual particles real physical things, or are they just a convenient mathematical trick, a way for our equations to account for the vacuum's fuzzy energy? Some physicists argue they are merely terms in a calculation, not entities you could ever trap in a box. Others point to effects like Hawking radiation and say, if something produces real particles that we can detect, then the process that creates them must be physically real in some sense. The line between a useful calculation and tangible reality becomes incredibly blurry. Experiments continue to push this boundary, trying to design ways to make these fleeting fluctuations manifest more directly, perhaps by using incredibly intense lasers to shake the vacuum so hard that virtual particles are forced to reveal themselves. The mystery is not just about what these particles are, but what their existence tells us about the nature of reality itself. Is the universe fundamentally fuzzy, a realm of probabilities and temporary loans where even nothingness is alive with transient creation? The ghostly fingerprints of virtual particles are not just theoretical. We can reach out and feel their push. This is the Casimir effect, a direct and elegant handshake between the quantum world and our own. Take two perfectly smooth, uncharged metal plates and place them parallel to each other in an otherwise perfect vacuum, separated by a gap tinier than the width of a human hair. Classically, nothing should happen, but in our quantum reality, an invisible force gently pulls them together. Why? Because the vacuum between them is different from the vacuum outside. In the open space, virtual particles of all possible wavelengths can flicker into existence. But in the narrow gap between the plates, only certain wavelengths can fit, like specific musical notes resonating in a pipe. This restriction means there are fewer possible virtual particle fluctuations between the plates than outside them. The greater pressure from the outside virtual particles pushes the plates inward. It is a literal, measurable force generated by nothing but the restless energy of empty space itself. first predicted in the 1940s and measured with increasing precision since. The Casimir effect is our most direct laboratory proof that the quantum vacuum is real, dynamic, and powerful. But what if we could do more than just restrict the vacuum? What if we could stir it like dragging a spoon through thick honey? This leads to an even stranger phenomenon, the dynamical Casimir effect. Imagine taking one of those mirrors in the Casimir experiment and moving it, not slowly but incredibly fast, shaking it back and forth at nearly the speed of light. Such rapid motion would violently disturb the quantum vacuum around it. The theory predicts that this agitation could pluck real, detectable photons, particles of light, right out of the void. The virtual particle pairs that usually annihilate each other instantly get shaken apart by the mirror's violent motion, becoming real before they can cancel out. For decades, this seemed like pure theory, a thought experiment impossible to test. How do you move a physical mirror that fast? Then, in 2011, a team of physicists performed a brilliant trick. They didn't move a physical mirror. They created an electrical mirror by using a superconducting circuit and rapidly changing its properties, which mimics the effect of a mirror moving at a significant fraction of light speed. And they did it. They measured the faint microwave photons that were created from the quantum vacuum. They had literally made light from nothing. This astonishing verification opens a door to a profound idea. The vacuum is not just a static background, it is a responsive medium. If you excite it in the right way, you can extract real particles from it, turning fleeting fluctuations into permanent pieces of our reality. It hints that all the matter and energy we see around us might have ultimately sprung from similar, universe-shaking disturbances in the primordial vacuum at the dawn of time. The emptiness, it seems, is a reservoir of potential waiting for the right kind of shake to turn possibility into substance. But if shaking the vacuum can create light, what happens when you are the one being violently shaken? This leads to one of the most dizzying predictions in all of physics, the Unruh effect. Imagine you are an astronaut floating in the deepest, darkest, most perfect vacuum of interstellar space. To you, the void is cold, black, and utterly empty. You feel nothing. Now, imagine you fire your rockets, accelerating through that same empty space at a tremendous, constant rate. According to the work of physicist William Unruh, your experience would change completely. You would no longer feel a cold nothingness. Instead, your spaceship would be bathed in a faint, warm glow of radiation. Your particle detectors would click, registering a sea of real photons and particles where there were none before. Yet, a second astronaut, coasting past you without accelerating, would still see and measure a perfect, empty vacuum. So who is right? Is the radiation real or not? This is not a trick. It is a direct consequence of marrying quantum field theory with Einstein's theory of special relativity. Acceleration warps an observer's perception of spacetime itself, effectively creating an event horizon behind them, much like the one around a black hole. From the accelerating perspective, the ever-present quantum fluctuations of the vacuum get stretched and distorted, appearing as a thermal bath of real particles. The faster you accelerate, the hotter this phantom glow becomes. It is a relativistic cousin to Hawking radiation, where acceleration replaces gravity. The staggering implication is that particle existence itself may not be absolute. What one observer measures as a bustling crowd of real particles, another might measure as serene nothingness. It forces us to ask what is truly real. Is reality defined by the universe or by how we move through it? This strikes at the heart of Einstein's equivalence principle, the idea that acceleration and gravity are locally indistinguishable. If an accelerating observer sees heat from the vacuum, does an observer standing still on Earth, feeling the acceleration of gravity, also see a thermal glow? In principle, yes, but here lies the experimental nightmare. To feel even a 1-degree warmth from Unruh radiation, you would need to accelerate at a quadrillion times the force of Earth's gravity. Creating such conditions, even for a subatomic particle, is a monumental challenge that pushes our technology to its absolute limits, yet the pursuit is crucial. Verifying the Unruh effect would not just confirm another weird quantum prediction. It would fundamentally challenge our notion of an objective reality, suggesting that the very particles that make up our world might be phantoms, conjured into existence by our own motion through the silent, seething quantum sea. This relativistic mirage of particles hints at a vacuum that is far more pliable than we ever thought. It can be stirred, shaken, and even polarized. This is the next deep mystery. The quantum vacuum is not a passive bystander to the forces of nature. It actively responds to them, bending and reshaping itself in profound ways. This effect is called vacuum polarization. Picture a single, isolated electron suspended in the void. Classically, it has a specific electric charge that creates a specific field around it. But in the quantum world, that electron is constantly surrounded by a seething cloud of virtual particle-antiparticle pairs, particularly electrons and their antimatter twins, positrons. Normally, these pairs flicker in and out randomly. However, the electron's own electric field disturbs this dance. It acts like a powerful magnet near a pile of iron filings. The virtual positrons, being positively charged, are slightly attracted toward the central electron. The virtual electrons, being negatively charged, are slightly repelled. For that fleeting instant of their existence, the vacuum around the real electron becomes polarized. It develops a subtle charge separation. This polarization cloud effectively screens or masks the electron's true, bare charge. From a distance, another particle feels a slightly weaker charge than what exists at the very core. This is not just a theoretical idea. It is the bedrock of quantum electrodynamics, our most precisely tested theory. Because of vacuum polarization, the strength of the electromagnetic force, encapsulated in the fine structure constant, is not actually constant. It changes or runs with energy. When two particles collide at extremely high energies, getting very close together, they penetrate this screening cloud. They feel a stronger, more naked charge. At lower energies, they feel the more shielded, effective charge. This running constant is a prediction of QED that has been verified to astonishing precision. But what happens when you push this effect to its absolute limit? Imagine an electric field so monstrously strong that it doesn't just polarize the virtual particles, it rips them apart permanently. This is the realm of supercritical fields. Near the nucleus of an atom with an enormous number of protons, the electric field can become so intense that the energy barrier keeping the vacuum stable collapses. In this zone, the vacuum undergoes a phase change. It spontaneously creates real electron-positron pairs from nothing. The positron is ejected while the electron is captured by the nucleus, all without any external input. The vacuum, in a sense, breaks down and boils. This has been theorized for decades, and there is strong experimental evidence from collisions involving heavy elements like gold or lead. It suggests that empty space has a critical point, a threshold of stress beyond which it ceases to be empty in any conventional sense. It becomes a factory for real matter, a place where the line between virtual fluctuation and permanent creation is irrevocably crossed. This leads us to a staggering possibility. If we could concentrate enough energy in one place, could we trigger a larger, more catastrophic phase transition in the vacuum itself, rewriting the rules of physics in a bubble of new reality? This spontaneous creation of matter from the void points to a deeper layer of structure. The quantum vacuum is not a uniform blank slate. It is filled with invisible fields, each with its own rules and energy. Among them, one field stands apart, not for being zero, but for being everywhere at once. This is the Higgs field. Unlike the electromagnetic field, which is zero when there is no light, the Higgs field has a constant, non-zero value in every cubic centimeter of the universe, even in the deepest vacuum. This baseline value is called its vacuum expectation value. Imagine walking through a room filled not with air but with a strange, invisible syrup. You would move slower with more resistance. That is essentially what the Higgs field does to certain fundamental particles. As particles like quarks and electrons move through the cosmos, they interact with this omnipresent Higgs field. That interaction is what we experience as mass. Without this field permeating the vacuum, all these particles would zip around at the speed of light, weightless, and atoms could never form. The Higgs mechanism is the reason there is stuff instead of just energy. But this beautiful explanation opens a mystery so severe it keeps physicists awake at night. The question is, why does the Higgs field have the specific value it does? Why is the syrup exactly this thick? The problem is one of stability. In our theories, the mass of the Higgs particle itself is incredibly sensitive to quantum corrections. Virtual particles from all other fields, especially the immensely heavy ones at the highest energy scales, should contribute to the Higgs mass, pushing it up toward the Planck scale, the energy where gravity becomes as strong as the other forces. That scale is about a quadrillion times heavier than the Higgs mass we measure. To get the tiny, precise value we see, there would have to be an almost miraculous cancellation, a fine-tuning of parameters to 1 part in a quadrillion. This is the hierarchy problem. It feels like balancing a pencil on its tip in a hurricane and expecting it to stay upright for billions of years. The universe seems unnaturally, suspiciously stable. One proposed solution is supersymmetry, an elegant theory that posits every known particle has a superpartner. These partner particles would provide opposite quantum corrections to the Higgs mass, naturally cancelling out the huge numbers and stabilizing the vacuum without fine-tuning. But here is the catch. We have not found any of these superpartners at the energies we have probed. Their absence means that if supersymmetry is real, it is broken at a higher energy, and the delicate cancellation is once again thrown into question. This ties directly back to the terrifying idea of the false vacuum. The stability of our entire universe, the very masses of the particles that build us, hinges on the precise value of this one field. Calculations suggest that the Higgs vacuum expectation value we live with places our cosmos in a precarious, metastable state. We might be in that shallow dip on the hillside. A shift in the Higgs value could mean a transition to a new vacuum where atoms disintegrate. So the mystery of the Higgs value is not an academic curiosity. It is a question about the ultimate fragility of existence. Why is the vacuum shaped just so, allowing for stars, planets, and life? Is it through a sublime natural mechanism we have yet to discover, or through a staggering, unlikely accident? The precarious balance of the Higgs field is mirrored by another, even more subtle tension within the heart of the atom itself. Deep inside every proton and neutron, the strong nuclear force holds quarks together in a chaotic, swirling dance. The quantum vacuum of this force, described by a theory called quantum chromodynamics, possesses its own strange and silent mystery. The equations allow for a term that would violate two fundamental symmetries of nature simultaneously: charge symmetry, which swaps particles for antiparticles, and parity symmetry, which flips left and right. This CP-violating term in the strong force vacuum would have a startling consequence. It would cause the neutron, the neutral particle in every atomic nucleus, to have a slight electric dipole moment. Think of the neutron as a tiny, perfect sphere of neutral charge. This CP violation would distort that sphere, giving it a positive end and a negative end like a microscopic battery. We have looked for this distortion with incredible precision, and we have found nothing. The neutron's electric dipole moment is so small it might as well be zero. This glaring absence is the strong CP problem. Why does the strong force vacuum seem to perfectly respect these symmetries when nothing in the theory demands it? It is another case of suspicious, unexplained fine-tuning. The most elegant solution proposes a new character in our cosmic story, born directly from the vacuum's need to settle into a stable state. This character is the action, a hypothetical particle so light and shy it could be streaming through you right now by the trillions. The idea is beautiful. Imagine the parameter that controls this CP violation is not a fixed number, but a field that permeates all of space, much like the Higgs field. In the early universe, this field could have been set to any value. But as the cosmos cooled, the theory suggests this field would naturally relax, like a ball rolling down a hill, settling into the lowest energy state where CP symmetry is preserved. That settling process would produce ripples in the field itself. Those ripples are the actions. They are the cosmic sigh of the strong force vacuum finding its perfect, symmetric balance. What makes this idea electrifying is that actions, if they exist, would be perfect candidates for dark matter. They would have been created in vast numbers in the early universe. They are neutral, they interact incredibly weakly with normal matter, and they would be cold, moving slowly to help clump galaxies together. So here, a deep mystery of the quantum vacuum, why the strong force is so symmetric, offers a direct and elegant solution to the greatest puzzle in cosmology. What is the universe's missing mass? The search for the action is now a major frontier, using ultra-sensitive experiments in deep underground labs and even strong magnetic fields to try and coax this ghostly particle, this child of the vacuum, into revealing itself. Finding it would be a monumental triumph, proving that the emptiness itself holds the keys to the structure of everything we see. The action emerges from a vacuum seeking perfect symmetry, but sometimes perfection must be broken for a universe to take shape. This is the profound idea of spontaneous symmetry breaking. The laws of physics themselves can be perfectly symmetric, yet the state the universe settles into, the vacuum, chooses a specific, less symmetric configuration. Think of a pencil balanced perfectly on its tip. The situation is symmetric in every direction, but the pencil cannot stay that way. It must fall. When it does, it picks one specific direction, breaking the rotational symmetry. The laws of gravity didn't change, but the final state did. This is not a flaw, it is a creative act. In the early, searingly hot moments after the Big Bang, the universe was in a state of perfect symmetry. The electromagnetic force and the weak nuclear force were unified as a single, elegant electroweak force. Particles like the W and Z bosons, which mediate the weak force, and the photon, carrier of light, were all massless and indistinguishable. But as the cosmos expanded and cooled, it crossed a critical temperature threshold. The Higgs field, permeating all of space, underwent a phase transition. It shifted from a symmetric state of zero value to a non-zero value everywhere, like water freezing into ice. This spontaneous breaking of the electroweak symmetry gave mass to the W and Z bosons while leaving the photon massless. In that moment, one unified force fractured into the two distinct forces we see today, and particles gained the property of mass. The vacuum we inhabit is the fallen pencil, the frozen ice. The deeper mystery is whether this was the only break. Many physicists suspect our vacuum is the result of a series of cosmic freezes. Grand unified theories propose that at even higher energies, the strong nuclear force was also merged with the electroweak force in a single, sublime symmetry. As the universe cooled further, that grand symmetry broke, then the electroweak symmetry broke later. Each phase transition etched a new set of rules into the fabric of reality, locking in the constants and forces we measure. This leads to a staggering possibility. The specific vacuum we live in, with its particular strengths for forces and masses for particles, might not be the only possible outcome. It could be just one of a vast landscape of possible frozen states, one valley among countless others in a cosmic terrain of potential realities. Did random quantum fluctuations during cooling steer us into this particular valley, this specific vacuum that allows for atoms and life? If so, the emptiness around us is not a fundamental stage. It is a historical artifact, a frozen moment from a more symmetric past. holding within its quiet fields the broken pieces of a perfect beginning. This broken symmetry of our vacuum may hold the answer to the most existential question of all. Why does anything exist? When the universe was born in the Big Bang, energy should have condensed into equal amounts of matter and antimatter. For every proton, there should have been an antiproton, for every electron, a positron, and when matter meets its antimatter twin, they annihilate in a flash of pure energy. If the early cosmos had been perfectly balanced, every particle would have found its opposite, and the entire universe would have dissolved back into a featureless sea of radiation. There would be no stars, no planets, no us, yet here we are in a cosmos made almost entirely of matter. Photons outnumber protons by about 1 billion to 1, the faint afterglow of that near-total annihilation. But a tiny 1 in 1 billion sliver of matter survived. Where did that overwhelming advantage come from? This is the Baryon asymmetry problem, and its solution must be written in the physics of the universe's first moments. In 1967, physicist Andrei Sakharov outlined the 3 conditions needed to create a matter-dominated universe from a symmetric beginning. First, there must be processes that violate the conservation of baryon number. Baryons are particles like protons and neutrons, and their number was thought to be a fixed tally. To create a surplus of matter, you need reactions that can change that tally, producing more baryons than antibaryons. Second, there must be a violation of both charge symmetry and parity symmetry, what we call CP violation. This ensures that the processes that create matter work slightly differently than those that create antimatter, introducing a fundamental bias into the laws themselves. We have seen tiny amounts of CP violation in particle decays, but nowhere near enough to explain the cosmic scale imbalance. Third, and crucially, all of this must happen during a departure from thermal equilibrium. In a perfectly hot, uniform soup, every creation event would be balanced by an annihilation event. You need a cosmic shudder, a phase transition where the rules change abruptly, freezing in a surplus before the system can rebalance. This is where the quantum vacuum of the early universe becomes the ultimate crucible. As the cosmos expanded and cooled, it likely underwent a series of dramatic phase transitions, like water freezing or steam condensing. Each transition represents the moment a field, like the Higgs field, settled into its new vacuum state. During these violent, non-equilibrium shifts, the conditions could have been perfect for Sakharov's recipe. Hypothetical heavy particles predicted by grand unified theories could have been created and then decayed, their CP-violating decays favoring matter over antimatter. Or the changing vacuum itself, bubbling with new domains as it settled, could have catalyzed reactions that tipped the scales. The quantum fluctuations in those first instants were not just tiny wrinkles. They were the architects of cosmic fate. The specific vacuum we emerged into, with its specific broken symmetries, didn't just give particles mass. It may have also imprinted upon the cosmos its very substance, deciding that there would be something rather than nothing. The mechanism remains one of physics' greatest hunts, hidden in the seething physics of a vacuum that existed for less than 1/1000th of a second after everything began. Those first instants did more than just tip the matter-antimatter scales. They left a permanent imprint on the sky, a blueprint for everything to come. This is one of the most breathtaking connections in all of science, linking the smallest quantum whisper to the grandest cosmic architecture. The theory of cosmic inflation proposes that a fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion, driven by a hypothetical field called the inflaton. As this inflaton field rolled down its energy hill, it stretched space itself by an unimaginable factor, smoothing and flattening the cosmos. But here is the crucial part. Even in this primordial vacuum, the inflaton field was not perfectly smooth. It was subject to the same quantum uncertainty as every other field. microscopic fluctuations, tiny ripples of more or less energy, were constantly flickering in and out of existence. Normally, these quantum jitters are fleeting, vanishing as quickly as they appear. However, during the violent expansion of inflation, something miraculous happened. Space stretched so rapidly that these subatomic ripples were pulled apart faster than they could cancel themselves out. A fluctuation that was smaller than a proton in one instant was, in the next, stretched to a size larger than our observable universe. The quantum became classical. Frozen into the fabric of spacetime itself, these amplified vacuum fluctuations became slight variations in the density of matter and energy across the cosmos. Slightly denser regions had a bit more gravitational pull, attracting more matter over billions of years. Slightly less dense regions became the great cosmic voids. We can see this ancient fingerprint today. The cosmic microwave background, the afterglow of the Big Bang, is not perfectly uniform. When we map its temperature with satellites, we see a mottled pattern of hot and cold spots, differences of mere millionths of a degree. That map is not static noise. It is a direct photograph of those primordial quantum fluctuations, stretched across the entire sky and frozen in time when the universe was only 380,000 years old. Every galaxy cluster, every spiral arm, every star, and every planet owes its ultimate origin to those microscopic quantum ripples in the inflattened field's vacuum. The structure of our universe on the largest scales was literally seeded by the irreducible quantum fuzziness of nothingness. It means the quantum vacuum is not just the stage for our existence. It is the architect, but if the vacuum's fluctuations can seed entire galaxies, could they also be responsible for the very act of observation? This brings us to one of the most profound and unsettling questions in all of science, the measurement problem. In the quantum world, particles exist in a haze of probabilities called a wave function. An electron is not in one place or another until you measure it. Upon measurement, this fuzzy cloud of possibilities collapses into a single, definite reality. The question that has haunted physicists for a century is simple: what exactly constitutes a measurement? Is it a conscious observer, the interaction with a large, classical instrument, or could it be something more fundamental woven into the fabric of space itself? Some interpretations of quantum mechanics, known as objective collapse models, propose that wave function collapse is not triggered by observers, but happens spontaneously and randomly. There is a small, inherent probability for a superposition to simply resolve itself into one state over time. But what could be the source of this randomness? One compelling candidate is the quantum vacuum. Imagine the vacuum's ceaseless fluctuations as a kind of universal background noise, a static hiss underlying all of reality. In objective collapse models, this vacuum noise could be the physical mechanism that constantly jostles quantum systems, eventually tipping them from a state of many possibilities into a single, definite outcome. The vacuum wouldn't just be a stage for particles, it would be an active participant in creating the classical world we perceive from the quantum fog. This idea finds an even more radical expression in a fringe but fascinating theory called stochastic electrodynamics. Its proponents ask a revolutionary question: what if quantum mechanics isn't fundamental at all? What if it emerges from a purely classical world? Their proposal is that empty space is filled with a real, physical random zero-point field, a classical version of the quantum vacuum's energy. This all-pervading sea of random radiation would constantly buffet every particle, giving them a permanent jitter. When you work through the math of how particles would behave while being shaken by this universal background noise, something incredible happens. The equations begin to reproduce the famous results of quantum mechanics, like the uncertainty principle and quantization of energy levels. From this perspective, the weirdness of quantum theory, the probabilities, the wave functions, isn't a description of reality's core, but a statistical account of how objects behave when immersed in this churning classical vacuum medium. While most physicists view stochastic electrodynamics as an incomplete alternative to mainstream quantum theory, its value is profound. It forces us to ask if the vacuum could be the ultimate decoherence environment. Decoherence is the process by which a quantum system loses its weird superposition states by interacting with its surroundings, effectively making it classical. The vacuum, with its infinite degrees of freedom, could be the final and most effective environment, the reason why we never see cats that are both alive and dead. The measurement problem might not need a conscious observer. It might simply need the relentless, whispering chaos of empty space to constantly nudge possibility into fact, sculpting the solid world from the quantum sea one random fluctuation at a time. The relentless jitter of the vacuum might even leave its mark on the universe's ultimate speed limit. We are taught that the speed of light in a vacuum is a constant and unwavering pillar of physics. But what if the vacuum itself has a texture so fine it could subtly bend that rule? At the unimaginably tiny Planck scale, where quantum mechanics and gravity are thought to collide, our smooth picture of spacetime may shatter. Here, the vacuum is theorized to be a churning quantum foam, a seething sea of virtual black holes and wormholes with geometry that constantly fluctuates and froths. In this realm, the very concepts of here and there break down. If this foam is real, it would give the vacuum a granular structure like a superfine mist. And just as light slows down when passing through air or water, could these quantum grains affect a photon's journey? Some speculative models of quantum gravity suggest they might. The idea is that photons of different energies might interact with this foam in slightly different ways. A very high-energy gamma-ray photon, with its incredibly short wavelength, might feel the lumpiness of the foam more than a low-energy radio wave. This could cause the gamma-ray photon to travel along a slightly more tortuous path through the quantum graininess, arriving a minuscule fraction of a second later than its lower-energy counterpart. The variation would be astonishingly small, but the implication is monumental. It would mean the speed of light is not a perfect constant in all conditions. It could have a tiny energy dependence imprinted by the vacuum's hidden architecture. To test this, astronomers turn to the most powerful explosions in the universe, gamma-ray bursts. These colossal detections, often billions of light-years away, send a torrent of photons across the entire electromagnetic spectrum racing toward Earth. If the quantum vacuum foam is real and affects light, the highest energy photons in that burst should stagger in just a hair behind the lower energy ones. By analyzing the arrival times of these photons with space telescopes, scientists are hunting for that delay. So far, no definitive signal has been found, placing ever tighter constraints on the possible models. But the search continues because finding that delay would be more than just a new observation. It would be our first direct experimental touch of the quantum structure of spacetime itself. The vacuum would be revealed not as a passive, empty stage, but as an active, granular medium that sculpts the journey of light itself, challenging a constant we thought was written in stone. The search for a delay in starlight echoes a much older quest. Over a century ago, physicists were convinced space was filled with a substance called the luminiferous ether. This static, invisible medium was thought to be the necessary carrier for light waves, much like air carries sound. The famous Michelson-Morley experiment in 1887 aimed to detect our planet's motion through this ether wind by measuring subtle changes in the speed of light. They found nothing. There was no wind, no drag, no preferred frame of reference. This null result was a shock that ultimately paved the way for Einstein's theory of relativity, which declared the ether unnecessary. Space itself could bend and stretch, and the speed of light was constant for all observers. The ether was dead. Yet here we are, speaking of a quantum vacuum that is seething with energy, that can be polarized, that can push plates together and even slow light in theory. So we must ask a provocative question. Is the quantum vacuum simply the ether of the 21st century, resurrected in a more sophisticated quantum form. On the surface, the parallels are striking. Both concepts describe space not as a true void, but as a something with physical properties. The old ether had a density and elasticity to propagate waves. Our quantum vacuum has an energy density, a permeability that affects virtual particles, and a structure that might even grain space-time. But the differences are profound, and they save the vacuum from the fate of the ether. The old ether was a classical, mechanical substance. It implied a universal rest frame, an absolute background against which all motion could be measured. The quantum vacuum is fundamentally relativistic. It is Lorentz invariant, meaning no experiment conducted entirely within a vacuum can detect your state of uniform motion. Whether you are still or moving at 99% of light speed, the vacuum looks the same to you. Its effects, like the Casimir force, are there for all inertial observers. There is no preferred frame, no cosmic wind to feel, so it passes the Michelson-Morley test with flying colors, yet the philosophical tension remains acute. What are we really talking about when we speak of the vacuum? Is it a tangible physical medium, a new kind of cosmic fluid with real properties like energy, density, and permeability? Or is it merely a convenient mathematical description, the abstract ground state of quantum fields, with no more independent reality than the number zero? This debate cuts to the heart of modern physics. If we treat the vacuum as a real something, it seems to solve immediate problems. It gives us a mechanism for the Casimir effect, a source for dark energy, a medium for inflation's fluctuations, and an environment for decoherence. It feels intuitive to say empty space is made of stuff, but this attribution creates monumental new problems. A real physical medium should have a rest frame violating relativity. Its enormous calculated energy density should have destroyed the universe. Its potential granularity challenges the constancy of light speed. By making the vacuum a substantive thing, we risk resurrecting the very ghosts Einstein banished. The most conservative stance is to say the vacuum is not a thing in itself, but a condition, the lowest energy configuration of quantum fields. All the activity we attribute to it, from virtual particles to zero-point energy, are just manifestations of the fields being in that particular state. The fields are the reality, the vacuum is just their quietest mode. Yet when we measure a force between two plates caused by that condition, it becomes very hard to deny that condition has physical consequences. Perhaps the answer lies in letting go of our classical intuition altogether. The quantum vacuum may be something entirely sui generis, a third category that is neither a mechanical substance nor a pure abstraction. It is a relativistic quantum entity with observable effects but no fixed substance, a set of possibilities that becomes tangible only through interaction. It is the modern ether not in its mechanics, but in its role as the fundamental canvas of reality, a canvas that is itself dynamic and full of hidden potential. To call it nothing is clearly wrong, but to call it a something may be asking the wrong question of a realm that operates by rules far stranger than any medium we have ever known. This tension between the vacuum as a medium and a mathematical state confronts its ultimate test at the edge of oblivion. A black hole's event horizon is where the quantum vacuum meets the most extreme gravity, and the result is a paradox that threatens to unravel physics. Stephen Hawking's great insight was to apply quantum field theory to this curved spacetime. Just outside the horizon, the intense gravity warps the vacuum so severely that virtual particle pairs, which normally annihilate instantly, get torn apart. One particle falls into the black hole while its partner escapes to infinity as real radiation. From our perspective, the black hole glows with a faint heat, slowly losing mass and energy. It evaporates. This Hawking radiation is a direct child of the vacuum's fluctuations, but here lies the catastrophe. Hawking showed this radiation is purely thermal, like the glow from a hot stove. It carries no information about the specific star, spaceship, or book that formed the black hole or later fell in. When the black hole finally evaporates completely, all that intricate quantum information about everything it ever consumed seems to vanish from the universe. This violates a sacred principle of quantum mechanics called unitarity, which states that information can never be destroyed. It can be scrambled but never erased. This is the black hole information paradox. For decades, it presented an either-or choice that pleased no one. Either quantum mechanics is wrong and information is lost, or general relativity is wrong and black holes do not have true event horizons. The stalemate suggested our understanding of the vacuum near such extreme gravity was fundamentally incomplete. A breakthrough, however, is emerging from the study of the vacuum's most subtle property, entanglement. Empty space is not just a sea of fleeting particles. Every point is quantum entangled with every other point. This intricate web of connections is what gives space-time its smooth, continuous geometry, according to new ideas like the AR=EPR conjecture. A black hole, then, is not just a hole in space. It is a knot of extreme entanglement. Recent work using the gravitational path integral, a tool to sum over all possible spacetime geometries, has revealed a startling possibility. As a black hole evaporates, calculations suggest that regions of spacetime far from the horizon, dubbed islands, become subtly connected to the black hole's interior through the vacuum's entanglement network. Information that seemed trapped inside the black hole is in fact encoded in these distant islands via the radiation that has already escaped. The Hawking radiation is not random noise after all. It is an encrypted message with a decryption key spread across the vacuum's entanglement structure. The event horizon becomes a kind of quantum computational surface, processing information through the vacuum itself. This hints at a radical vision. Spacetime and gravity may not be fundamental. They could be emergent phenomena like the wetness of water, arising from the vast, complex entanglement of the underlying quantum vacuum. A black hole's evaporation is then the slow unraveling and reweaving of this cosmic quantum fabric. The paradox forces us to see the vacuum not as a passive stage, but as a dynamic processor of quantum information, where geometry and entanglement are two sides of the same coin. Resolving what happens to a bit of information in a black hole may finally show us what empty space truly is. The entanglement that may resolve black holes points to a vacuum that is deeply interconnected, but is that connection the same everywhere? Our next mystery pulls the colossal problem of the cosmological constant down to a surprisingly human scale, asking if the vacuum's energy might change from place to place. For decades, we have measured the universe's accelerating expansion and assumed dark energy is perfectly uniform, a smooth, relentless pressure identical in every cubic light-year of space. But what if our cosmic neighborhood is special and we have been misreading the vacuum's signature? Mounting astronomical evidence suggests we might live in a bubble, not of higher density but of startling emptiness. It is called the KBC void or the local hole. Observations of galaxy distributions and the cosmic microwave background indicate that for nearly 1 billion light-years in every direction, the density of matter around our Milky Way is significantly lower than the cosmic average. We reside in a vast underdense region, a cosmic countryside surrounded by denser metropolitan clusters of galaxies. This alone is not impossible. The universe is lumpy. But the scale and emptiness of this void are statistically unusual, sitting at the edge of what our standard model of cosmology predicts. Could this giant hole in the cosmos be a clue? Some theorists propose an alternative. Perhaps the vacuum energy is not a universal constant after all. What if it varies in space tied to the density of matter around it? In regions of average density, like most of the universe, the vacuum energy has the value we measure as dark energy. But in an underdense region like our local void, the vacuum energy could be lower, even zero. From our peculiar vantage point inside this bubble of lower vacuum energy, we would measure a different expansion rate for the nearby universe than someone in a denser region would. This could potentially explain certain tensions in our measurements of the Hubble constant, the rate of cosmic expansion. It suggests dark energy might be an environmental effect, a property of the vacuum that emerges from its interaction with matter rather than a fixed background feature. This idea dovetails with another long-standing galactic mystery that also challenges a universal constant, but for a different force, gravity. For 50 years, astronomers have noted that stars at the outer edges of spiral galaxies orbit far too quickly. According to Newton's laws and the visible mass, these stars should be flung into intergalactic space. The mainstream solution is dark matter, an invisible halo of particles providing extra gravity. But a persistent alternative exists called modified Newtonian dynamics, or MUND. It proposes that on the scale of galaxies where accelerations become incredibly tiny, gravity behaves differently. Newton's law gets a small modification. While MUND is a purely phenomenological adjustment, some of its relativistic extensions attempt to ground it in the physics of spacetime itself. In these theories, the quantum vacuum is not a passive backdrop. Its response to gravity changes in low acceleration environments. The vacuum might polarize or develop subtle collective behaviors that effectively strengthen gravitational attraction on galactic scales without needing invisible matter. Think of it like this: a single magnet has a certain field, but if you place it in a medium filled with tiny iron filings, the overall magnetic influence changes shape and reach. If the vacuum itself acts as a responsive medium to gravity, then in the weak field outskirts of a galaxy, its collective reaction could mimic the effects of dark matter. This is highly speculative and faces significant challenges, particularly in explaining the behavior of galaxy clusters, but its philosophical implication is profound. It asks whether the vacuum's properties, its energy, its response to gravity, are truly immutable constants, or if they are dynamical and shaped by their environment. Are we applying the rules of our local cosmic void to the entire universe? The vacuum catastrophe may not be one problem, but two: a global mismatch in energy density, and a local mystery of why our piece of the cosmos seems so oddly empty. Both push us toward the same unsettling question: is the silent quantum sea uniform, or does it have tides and currents, changing its nature from one region of space to another, making our view of the cosmos fundamentally provincial? These currents in the vacuum, if they exist, must eventually smooth out into a final, fundamental grain. The ultimate texture of reality is not set by galaxies or atoms, but by nature's absolute smallest units of space and time. This is the Planck scale. The Planck length is about 10 to the power of -35 meters. The Planck time is the duration it takes light to cross that distance, a mere 10 to the power of -43 seconds. To grasp this scale, if you magnified an atom to the size of the observable universe, the Planck length would be roughly the height of a single tree. At this incomprehensibly tiny frontier, our two great pillars of physics, quantum mechanics and general relativity, collide in a storm of contradiction. Gravity, which shapes the cosmos, becomes a raging quantum force. Here, the smooth, geometric fabric of spacetime predicted by Einstein shatters. The quantum vacuum is theorized to dissolve into a seething, chaotic froth. Physicist John Wheeler called this quantum foam. In this frenzied sea, the very concepts of here and there, before and after, lose all meaning. Spacetime is no longer a stable stage. It is a turbulent, probabilistic foam where geometry fluctuates wildly. Microscopic wormholes, tunnels connecting different points, would blink in and out of existence. Virtual black holes with masses near the Planck scale would spontaneously form and evaporate in a fleeting instant. The vacuum at this level is not a calm, empty medium. It is a boiling, probabilistic froth of spacetime itself, the mystery is profound. What is the vacuum truly made of at its most fundamental level? Is it woven from tiny, vibrating strings, as string theory suggests? Or is it built from discrete loops of quantized space, as in loop quantum gravity? Or is it something our mathematics cannot yet describe? The challenge is that probing this regime directly seems utterly impossible. To create a particle with enough energy to resolve the Planck scale in an accelerator, you would need a collider the size of our galaxy. So we must become cosmic detectives, looking for subtle imprints this foam might leave on the universe. One ingenious approach listens to the cosmos's most precise metronomes, pulsars. These spinning neutron stars emit beams of radio waves with the regularity of atomic clocks. As these waves travel billions of light years to Earth, they pass through the quantum foam of the vacuum. If spacetime is grainy at the Planck scale, it should very slightly scatter these radio waves, introducing a faint, random noise into their incredibly regular pulses. By analyzing the timing of signals from many pulsars across the sky with vast radio telescope arrays, scientists are hunting for this specific type of noise in the data. So far, the clocks remain eerily perfect, telling us that if foam exists, its grains are even finer than we thought, or its nature is far stranger. Another frontier is in the lab, using not massive energies but exquisite precision. Quantum optics experiments with entangled photons or super-sensitive interferometers might detect minuscule fluctuations in the vacuum structure. The idea is to use the quantum properties of light itself as a probe, sensing if the path it takes through empty space is subtly altered by a foamy texture. Finding any signature would be a revolution. It would mean that what we perceive as smooth, continuous emptiness is an illusion, an average over a reality that is fundamentally chunky and chaotic. The quantum foam is the final mystery of the vacuum substance, asking what the canvas of reality is woven from, thread by thread, at the very bottom of existence. That chaotic quantum foam might be the final frontier of physics, but it also hints at a breathtaking possibility for our future. What if we could not just observe the vacuum's properties, but engineer them? This brings us to one of the most thrilling speculative ideas in all of science, a concept ripped from science fiction that is grounded in real equations, the Alcubierre warp drive. In 1994, physicist Miguel Alcubierre asked a brilliant question. Einstein's theory of general relativity forbids objects from moving through space faster than light. But what if, instead of moving through space, you moved space itself? His solution was a geometric bubble. Imagine a spacecraft sitting inside a flat region of spacetime, like a passenger in the center of a moving sidewalk. The drive would contract the fabric of spacetime directly in front of the ship, pulling the destination closer. Simultaneously, it would expand spacetime behind the ship, pushing the starting point farther away. The ship itself remains motionless inside this warp bubble, experiencing no acceleration forces, while the bubble itself carries it along at speeds that could, in theory, exceed light speed. It is a loophole in relativity, using the malleability of spacetime as a propulsion system. But there is a monumental catch. To create this warp bubble, you need a very special kind of fuel. The mathematics demand what physicists call exotic matter, a substance with negative energy density. Normal matter, everything we are made of, has positive energy density. It warps spacetime in the familiar way that creates gravity, bending it inward. Negative energy density would warp spacetime in the opposite direction, creating a kind of anti-gravity or repulsive effect needed to expand space behind the bubble. This is where our journey through the quantum vacuum comes full circle. We have already seen negative energy density in action. Remember the Casimir effect. The region between those two plates, where certain virtual particle fluctuations are restricted, actually has a lower energy density than the surrounding vacuum. In a very real sense, that gap possesses negative energy relative to empty space. the quantum vacuum demonstrates that negative energy density is not just a mathematical fantasy, it is a permitted quantum effect. So the raw ingredient for a warp drive exists in principle in the seething activity of empty space. The problem is one of staggering scale and control. The amounts of negative energy required by Alcubierre's original design are astronomical, equivalent to converting the mass of Jupiter or even a large star into pure exotic matter. Later refinements have reduced the requirement dramatically, but it is still far beyond any technology we can conceive. Furthermore, there are serious stability issues. The warp bubble might be impossible to control or even form in the first place. Information and particles might not be able to enter or leave the bubble, trapping the crew in a helpless shell. Some calculations even suggest the leading edge of the bubble would accumulate lethal levels of radiation and particles, vaporizing anything at the destination upon arrival. Yet the idea persists as a beacon. It frames the ultimate mystery of the quantum vacuum. Can we ever learn to manipulate its deepest properties to sculpt spacetime itself using the energy hidden within nothingness? The vacuum is no longer just a subject of study, it becomes the ultimate engineering material. Mastering it would mean mastering the geometry of the universe, turning the silent, seething quantum sea into a highway for the stars. It transforms the greatest emptiness into the key to our cosmic destiny. The dream of engineering spacetime begins with understanding how to coax energy from the void. And one of the most puzzling clues comes from a simple glass of water. In a lab, scientists can create tiny flashes of light from sound. This is sonoluminescence, a phenomenon where powerful sound waves sent through a liquid create and violently collapse microscopic bubbles. In the final instant of collapse, just before the bubble vanishes, it emits a brilliant pinpoint flash of light, sometimes blue, sometimes white. For a fleeting trillionth of a second, the center of that collapsing bubble is hotter than the surface of the sun and under pressures greater than the ocean's deepest trenches. The question is, where does that intense energy come from? The mainstream and widely accepted explanation is a process called thermal Bremsstrahlung. As the bubble collapses, it heats the gas and vapor inside to such an extreme that it forms a tiny, dense plasma. The charged particles in this superheated soup slam into each other, and this violent deceleration releases energy as a flash of light. It is essentially creating a star in a jar, scaled down to the width of a human hair. The physics, while complex, fits within our understanding of thermodynamics and plasma physics. Yet, the sheer intensity of the flash has led some researchers to propose a far more radical idea. Could this process be tapping directly into the quantum vacuum's zero-point energy? The hypothesis is controversial and sits far outside the scientific consensus, but it is tantalizing. The thinking goes like this: the violent, ultra-fast collapse of the bubble might be creating conditions so extreme that it disturbs the local quantum vacuum, much like the shaking mirror in the dynamical Casimir effect. In that final moment of implosion, spacetime itself could be squeezed and jolted, forcing virtual particle pairs in the vacuum to convert into real photons, literally squeezing light from the emptiness. It would be a form of modern alchemy, turning sound energy into a shockwave that milks the quantum vacuum for light. Proponents point to certain anomalies in the timing and spectrum of the light as possible hints of a non-thermal quantum process. The vast majority of physicists remain deeply skeptical, seeing no need to invoke exotic vacuum energy when classical plasma physics provides a robust explanation. The temperatures and densities, while extreme, are still many orders of magnitude below what would be needed to manifest significant quantum gravitational effects or truly engineer the vacuum structure. Yet, the enduring mystery of sonoluminescence serves a vital purpose. It is a physical, tangible phenomenon that forces us to ask where the boundary lies between known physics and the hidden potential of the vacuum. It is a laboratory-scale echo of the universe's most violent events, a miniature implosion that, for an instant, creates conditions so severe they blur the line between the classical and quantum worlds. Whether it is a direct window into vacuum energy or not, it symbolizes the human quest to probe the limits of emptiness, to take something as mundane as sound in water and use it to interrogate the fundamental energy of the cosmos. It reminds us that the keys to the universe's greatest secrets might be hiding not only in distant quasars or particle colliders, but in the fleeting, brilliant death of a bubble in a beaker. That fleeting flash in a beaker is a whisper of the vacuum's hidden activity, but its ultimate purpose might be far grander than we ever dreamed. The quantum vacuum could be the universe's most powerful computer. This is not a metaphor from science fiction, but a serious theoretical framework emerging from our deepest puzzles about black holes and information. The idea begins with the holographic principle, one of the most radical concepts in modern physics. It suggests that all the information needed to describe everything within a three-dimensional volume of space, every star, every atom, every ripple of light, can be perfectly encoded on a two-dimensional surface that surrounds it, like a cosmic barcode painted on a distant shell. Think of a three-dimensional movie projected from a flat, two-dimensional screen. The holographic principle says reality might work the same way. The three-dimensional world we experience could be a projection from information stored on a vast, distant boundary. For a black hole, this makes profound sense. The maximum entropy or information content of any region of space is not proportional to its volume, as you might expect, but to the area of its surface. The vacuum inside that volume, with all its quantum fields and fluctuations, is not the primary reality. The true description is written on the surface. This transforms our view of the vacuum completely. It is no longer a container of stuff, but a dynamic, informational medium. The seething quantum foam, the entangled virtual particles, the fluctuating fields, all of this could be the visible manifestation of an unimaginably complex quantum computation happening on the boundary of space. The vacuum becomes the processor, and the evolving universe is the output. This ties directly into the black hole information paradox and the role of entanglement. The intricate web of quantum connections that permeates the vacuum is not just a side effect, it is the substrate. In models like the AD-S/CFT correspondence, a specific realization of holography, a gravitational theory in a volume of space is exactly equivalent to a quantum field theory without gravity living on its boundary. The chaotic quantum gravitational vacuum inside is dual to a highly ordered, entangled quantum system on the edge. The growth of space-time, the formation of galaxies, even the passage of time itself, could emerge from the way entanglement spreads and evolves in this boundary quantum computer. So the mystery sharpens into a breathtaking question. Are the laws of physics, gravity, electromagnetism, the nuclear forces not fundamental rules written at the beginning of time, but rather the emergent software of this cosmic computation? Is the universe we see the result of a calculation so vast it encompasses every particle and every force running on the hardware of the quantum vacuum? When a star forms, is that the output of a quantum algorithm resolving gravitational collapse? When you make a choice, is that a novel input causing a cascade of quantum updates across the entangled network? This vision turns reality inside out. We are not living in a static arena governed by fixed laws. We are participants in an ongoing cosmic computation where the vacuum is both the processor and the memory, and every event is a step in a calculation whose final answer we cannot yet see. This cosmic computation might be running more than one program at a time. Our universe, with its specific vacuum and precise constants, could be just a single thread in an infinite tapestry of realities. This idea flows directly from the theory of cosmic inflation, that same violent expansion that smoothed our cosmos and amplified quantum seeds might not have been a one-time event. Instead, it could be eternal, a relentless process where new pocket universes are constantly budding off from an ever-inflating background. Each of these bubbles would undergo its own version of the hot Big Bang, expanding and cooling into a separate cosmos. Crucially, as each bubble formed, the quantum fields within it would settle or freeze into a specific vacuum state. This is where the rules are written. The strength of gravity, the mass of an electron, the number of spatial dimensions, even the value of the cosmological constant. All of these fundamental properties are determined by which vacuum state a universe lands in. Our universe landed in a valley with 3 dimensions of space, 4 fundamental forces, and a cosmological constant just tiny enough to allow for galaxies. But in the bubble next door, the vacuum might have settled differently. There, gravity could be 1,000,000 times stronger, making stars burn out in an instant. Or electromagnetism could be so weak that atoms never bond. Or space could have 9 dimensions, 6 of them curled up so tightly we would never perceive them. The diversity is staggering. String theory, our most ambitious attempt to unify all forces, suggests a mind-numbing number of these possible stable vacuums, perhaps 10 to the power of 500. That is a 1 followed by 500 zeros, a number so vast it dwarfs every atom in our observable universe. This is the string theory landscape, a cosmic terrain of valleys and hills, each representing a different possible vacuum with different laws. Our universe is just one tiny, accidental garden in an infinite wilderness of possibilities. The philosophical implications are profound. It means the properties of our vacuum, which we have spent this entire journey investigating, may not be fundamental or finely tuned for life. They might simply be an environmental accident. We do not live in a special universe designed with perfect constants. We live in one that is habitable because, in a multiverse of every possible combination, some universes will, by pure chance, have the right numbers for stars and planets and life to form. We are here because our particular vacuum allows it. The countless other bubbles with inhospitable laws are empty of observers. This is the anthropic principle in its most expansive form. For scientists, this presents a monumental challenge. If other universes are causally disconnected from our own, forever beyond the cosmic horizon, can the multiverse ever be a scientific theory? How do you test something you can never observe, even in principle? Some look for possible imprints on our cosmic microwave background, a bruise from a collision with another bubble universe in the distant past. Others seek deeper mathematical consistency, arguing that if a theory like inflation or string theory naturally predicts a multiverse, and that theory solves other problems within our universe, then the multiverse gains indirect support. Yet for many, it feels like a retreat from explanation, swapping a mystery of fine-tuning for an infinite array of untestable worlds. Whether it is a profound insight or a philosophical dead end, the multiverse hypothesis is the ultimate expression of the quantum vacuum's creative potential. It suggests that emptiness is not just the source of our reality, but of all possible realities, a restless engine of genesis whose output is a cosmos of cosmoses, each with its own unique answer to the question, what can nothing become? The multiverse paints a canvas of infinite physical possibility, but leaves one final mystery untouched, a question that turns inward. What about the observer? What about the mind that contemplates the vacuum? This brings us to the most speculative and controversial frontier of all, the potential link between consciousness and the quantum void. At the extreme boundaries of thought, a few scientists and philosophers have dared to ask if the most complex phenomenon we know, our own awareness, could have roots in the most fundamental substrate of reality. The most famous of these proposals comes from physicist Roger Penrose and anesthesiologist Stuart Hameroff. Their theory, called orchestrated objective reduction, suggests that consciousness arises from quantum computations happening inside the neurons of our brain, specifically within structures called microtubules. These tiny protein scaffolds they propose could maintain quantum coherence where particles exist in superposition states long enough to perform complex information processing. The collapse of these quantum superpositions, according to Penrose, is not random but influenced by the geometry of spacetime itself, a process potentially linked to the fundamental Planck scale. This is where the quantum vacuum re-enters the picture. If such delicate quantum states exist in the warm, wet environment of the brain, they would be incredibly fragile, constantly jostled by their surroundings. Some extensions of this idea ponder whether the brain's neural environment could be uniquely shielded or tuned to interface with the vacuum's fluctuations. Could the mind's quietest moments, its states of deep awareness or intuition, involve a subtle interaction with the zero-point field, that sea of potential underlying everything? It is a staggering thought that the silent hum of the vacuum might not just shape galaxies, but also the very nature of subjective experience. It is crucial to state clearly that these ideas sit firmly outside mainstream physics and neuroscience. There is no experimental evidence that the brain sustains the kind of large-scale, long-lived quantum coherence the theory requires. The warm, chaotic interior of a neuron is considered an extremely hostile environment for such delicate quantum states, which we can only maintain under extreme laboratory conditions like near-absolute zero temperatures. Most researchers see consciousness as an emergent property of complex classical computation in neural networks, not quantum processes. Yet, including this speculative mystery serves a vital purpose. It shows us the extreme boundaries of human curiosity, where our questions about the outer cosmos collide with the inner cosmos of the mind. It highlights the profound and enduring enigma of whether the observer and the observed are truly separate. Is the mind, which can conceive of quantum fields and cosmic inflation, merely a passive product of the vacuum's physics, or could it, in some way we cannot yet imagine, be an active participant in that reality? The answer, if there is one, lies far in the future, but the question itself completes our journey through the 25 mysteries, reminding us that the ultimate nature of the vacuum is not just a puzzle of physics, but a mystery that touches the very essence of what it means to be and to be aware in this vast and whispering universe. From the spark of consciousness back to the silent sea of potential, our journey through 25 mysteries returns us to where we began, with a simple, staggering truth. The void is not empty, it is an unfinished symphony playing the score of existence itself. We have seen how this quantum vacuum is the source of the universe's greatest puzzles. Its missing energy may be the dark force accelerating cosmic expansion. Its microscopic fluctuations, stretched by inflation, seeded every galaxy and star. Its fields, through spontaneous symmetry breaking, dictated the masses of particles and the very forces that bind atoms. It may hold the key to dark matter in the form of actions, and its instability threatens a cosmic reset through vacuum decay. From the Casimir effect's gentle push to the fiery information processing at a black hole's horizon, the vacuum is not a backdrop, it is the protagonist. To truly understand it, to solve the riddle of its energy, to map its possible landscapes, to hear the whispers of its foam, is to achieve the ultimate goal of physics. It is the only path to unifying the quantum world with the realm of gravity, to grasping our cosmic origins from a single quantum tremor, and to foreseeing our ultimate fate in an accelerating or decaying cosmos. This pursuit is not merely academic, it is a fundamental quest to understand what reality is made of. So the next time you look up at the night sky, at the vast black spaces between the stars, remember you are not looking at nothing. You are gazing into a dynamic, mysterious quantum sea, a seething ocean of potential that birthed everything and holds the blueprints for all that is to come. Its secrets are waiting to be unraveled. Which of these 25 mysteries fascinated you the most? Let us know in the comments, and subscribe to join us as we continue our deep dives into the greatest mysteries of space.